My name's Steve Morley, and welcome to my poster. Together with my coworkers, I've been doing some work on predicting solar energetic particle access at medium Earth orbit. Hopefully this video will give a little more context to the poster and fill in some of the gaps. This overview of the poster is what you should be able to see through the AMS website. It's a summary of some of our work so far for a laboratory-directed research and development project. I'm going to start on the left-hand side of the poster, where we introduce the dataset we'll be using, which is from the GPS constellation, as well as the tools we're using for magnetic fields and particle tracing. Next, I'll move to the middle, where we present empirical models derived from GPS particle observations. This work is presented in more detail in the Student Symposium by Amanda Strickland. And while my team has been working to develop empirical models, we've also been developing simulations to predict particle access. The method we use is shown on the right-hand side with sample results. And then the final box introduces how we can improve our predictions of particle access by combining observations and simulations in an optimization framework. Not only will this improve our predictions of particle access, but it also allows us to improve our specification of different current systems. So, I'll start with the data set. The GPS constellation, pictured here, is in medium Earth orbit, distributed across 6 orbital planes inclined at around 55 degrees. A few years ago, energetic charged particle data measured by the CXD, combined X-ray dosimeter instruments on board the GPS satellites, were publicly released. A more recent update added cross-calibrated proton data. These data can be found via the data.gov portal, and this is what we'll use to measure proton flux and count rates from about 5 to in excess of 200 MeV. For our test particle modeling, we're going to have a magnetic field configuration to trace through. So for this, we're going to use the Space Weather Modeling Framework, as well as the Tsiganenko T96 semi-empirical model. To trace test particles through these fields in a time-varying fashion, we're going to use the SHIELDS PTM code. PTM just stands for Particle Tracing Model, and it was developed as part of SHIELDS, which was a large project at Los Alamos National Lab centered on predicting spacecraft charging hazards. The figure at the bottom here just shows a sample trajectory of an SEP traced backwards in time from a GPS satellite until it exited the magnetosphere. The PTM code is fully relativistic, and it supports tracing full particle motion as well as guiding center motion, and it can intelligently switch between the two modes. So, let's take a quick look at the data-derived models. So in the top panel here, we see the flux as a function of L and time at 30 MeV for one of our out-of-sample events. We've separated our training data from our test data, and the flux here is binned in time and L, and it combines all of the GPS satellites that were available at the time. The bottom panel shows the same data but normalized, and then we've removed everything that's below a background level. So what you can see here is as the color bar transitions down through white, we're crossing that 50% threshold, which is usually used as an heuristic for identifying the cutoff at a given energy. Okay, so over the top of that, we've plotted some observations that were algorithmically determined cutoffs, that's the yellow diamonds, and then the lines represent different models. The best of these models is a Bayesian ridge regression, which is a type of robust, probabilistic, multiple linear regression. So if you have the opportunity to see Amanda Strickland's poster in the Student Symposium, she has significantly more detail about this work. But just to summarize, we've developed an algorithm to robustly and automatically identify the cutoff L from CXD data. We fit a number of different models parameterized by geomagnetic activity and solar wind parameters. And the most promising of these is Bayesian ridge regression, partly because of the good performance, but partly because it brings uncertainties with it. And these are generally missing from empirical models of cutoff. We've also done some preliminary assessment of the model performance relative to our baseline Stormer model, which assumes a centered dipole, and a DST-based model presented by Paul O'Brien, which combined work by Lesky and Ogliore. So let's move on now to the numerical predictions. In this section, I'll be showing results that traced particles through the space weather modeling framework fields that we showed earlier. And we're tracing for each GPS satellite over 20,000 particles backwards in time from each location. The particles are traced for up to 5 minutes or until they leave the magnetosphere. And from these trajectories, we can determine whether the paths are allowed or forbidden. And allowed means that if you trace it backwards, it leaves the magnetosphere, and hence anything entering the magnetosphere on that path would reach the satellite. Okay, so once we have our allowed and forbidden trajectories, then we can do Liouville mapping from a source spectrum to predict the spectrum at the target. For our source spectrum, we want to use a measurement of the flux spectrum in a minimally shielded region. And so for this, we're using NS62, which was in the open field region at the time. And that's marked up here with this green curve. This is the predicted flux spectrum. Oh, this is the observed flux spectrum from NS62 at this time. The prediction from our simulations of what would be seen at NS57 is shown here in the blue. And NS57 is around here. It's an L of 5.7, and it's on the dawn side of the Earth. Okay, so just key features on this plot. There's also this barcode here at the bottom. Solid black means all trajectories are forbidden, and solid white means all trajectories are allowed. And it's a little easier to see why this is useful when we move around to NS71, which is on the night side at L of 5.2. And you can see here, now we have this hard lower cutoff here marked by the little triangle. And then we have this thick penumbral region where there's a significant fraction of the trajectories that are not allowed. And so you can see here, this is very dark gray to black. And then we transition up here to above 80% transmission. And so we have our estimated effective cutoffs, as well as predicted spectra. So what we're going to do with that then is we're going to move this into the space of what would be observed by the instrument. And so we do this by combining the predicted flux spectrum with the energy-dependent geometric factor for each channel. And then we estimate the counts, which are shown here on the right-hand side. And so you can see here we actually do very well at predicting the first 3 channels. And then we're a little off for the 2 highest energy channels. So this is our method and our example. So let's move now to how we might combine this with data to improve our estimates. So for this, we're not going to use the space weather modeling framework. We're going to switch to a much simpler semi-empirical model, and we're going to use the Sigonenko T96 model because it's built from modular current systems. That is, it has a ring current, it has a magnetopause current, it has Birkeland currents, and these are all added together to give a magnetosphere configuration. Okay, so our intent here is to optimize specific current system parameters to minimize the difference between our predicted counts and the observed counts. And we'll look at the flow chart for that in a little more detail soon. The figure below shows an example for NS71 again, but now tracing through the T96 field. And you can see we no longer have a hard cutoff within our energy range, and we no longer have a thick penumbral region. What we have over here is we have a clear deviation from the spectrum in the open region. So there's some shielding, but there's very much less. We have an effective cutoff near 30 MeV, whereas previously in the SWMF field, it was almost 50 MeV. And then on the right-hand side here, we have in gray, it's just a grayscaled version of the count rates that we showed in the previous section. And then the orange and blue are the results from our T96 simulations. And so you can see P1 has improved slightly, P2 is similar, P3 has gotten slightly worse, but it's still very close. P4 has improved substantially, P5 is very similar. And so you can see that the magnetic field definitely has a significant impact on the predicted count rates. So how can we use that to improve our predictions? Well, the optimization framework that I mentioned here starts with generating fields in this semi-empirical model. And that's important because we need a parameterized model so that we can optimize the parameters. And then we run through the method that I presented earlier. We trace our test particles, we obtain the flux at GPS, we do the Liouville mapping and obtain the counts. And then we can find the error between the count rates and the predictions. And this is our model loss. So then we can use this in an optimization fashion to update our parameter estimates and repeat until we've minimized that loss. And this gives us the best fit field configuration, which we can then use to predict cutoff rigidities or spectra anywhere. We can use the field for other things as well. And it also gets us optimized current system parameters so that we can better understand how these current systems are actually manifesting during our events. So to summarize, using data to optimize magnetic field models enables improved predictions and data-constrained estimates of current system parameters. And by using SEP trajectories for this, we're bringing global data instead of just local data. Anyway, if you have any questions about this, please feel free to get in touch, and I hope that you enjoyed this poster. All right, well, thank you very much.